I got my license in '77 when I was in Michigan, in Ann Arbor, and was WD8 MFC, then I was KB8BZ, then I was KC8B, and then when I moved to Oregon to work for HP, I was KR7C. So that's about the extent of it. This is the topic of today is, maybe I should start the projector, that would help.
Should we dim the lights?
Well, it's pretty bright,
so.
we'll see
Really
what
bright,
people think.
yeah.
You know, Eric's going to tape this, so if we can get by without dimming it too much, it'll do well on the blog site.
Okay, Mr. Epson.
That an HP projector? Or?
No, it's an HP used to make them, remember? I know. Come on.
Kick the plug.
Yeah, HP used to make cameras. They don't.
It's on.
Yeah, that's
It's
coming.
on, but we need to dim.
No, no, it's not very.
No, it's not. It's pretty bright.
Yeah,
It actually projects right through the screen. It's so intense.
Right through the screen.
You see it on the backside.
So
Wow.
maybe we should seat some people in the back too.
When I was in the Navy,
If you're dyslexic.
you can actually watch it on the
See
safe
people on the backside.
Who's dyslexic?
I was on an aircraft carrier. We used to project movies on the side wall. That's how powerful that projector was.
Come on.
Drill through that, but.
That's lavender. That's not lavender.
There we are.
Yeah. The plant.
All right, today's topic is HF terrain assessment. Basically, trying to understand how the local terrain around an antenna installation affects the propagation and what kind of propagation you can expect given that environment. So the overview for today is, I'm going to do a real quick review of HF skywave propagation.
Can you go back one slide, please, Dan?
Wow.
We're not getting very far.
Thank you, sir.
Yeah.
Be a long meeting. And that's a decent tower.
Yeah, that's the one I always wanted. So I'm going to do a quick review of HF skywave propagation, just for people who are maybe not so familiar with it, and just stealing from the antenna book. I'm going to talk about what terrain assessment really is, why we would do it, what information and tools are used that are available, the National Elevation Database for terrain data. MicroDem is a program to help us take that data and manipulate it so that HFT A, which is a program that's actually called High Frequency Terrain Assessment, written by N6BB, as we'll get to, takes that and then presents the data in a form that you can appreciate the effect of terrain on propagation. And I'll do a demo of all the tools and process. I have internet connection via cellular, so we'll be able to actually do some live stuff. And then I'll give some quite a number of examples and comparisons of some QTHs of the usual suspects around here, and then a conclusion. So the HF skywave propagation, which is to be differentiated from either ground wave, which is real local, or line of sight. We're talking about radio waves that go up into the ionosphere and then are reflected back to Earth. And it allows, well, as Ash was saying earlier, being able to use NVIS, which is nearly vertical incident skywave, is what that stands for. Basically, you're just going straight up with a low enough frequency. You can, and during the day, you can bounce signals right off that, and it would be basically go straight up into. You can go straight up from the transmitter right up into here, and then right back down again. Okay, or all around if you've got that if you've got a good bright sunny day. Actually, it doesn't have to be sunny on the ground; it just has to be day. This diagram really tries to show you that you can get a lot of pathways from a transmitter to any particular receiver, and the angles. What's really important from this to take away from this particular diagram is that there are various angles. There's quite a range of angles that signals come back to the Earth between any 2 points. And what we're going to be looking at it a lot, because that's an important part of trying to judge when and where a station should be able to communicate given angles of the predominant angles or average angles of incidence at any particular location. I'm not going to go any further into this. This is from the antenna book to give it credit.
Is it true to say that the up angle is the same as the down angle?
No, not necessarily, because the ionosphere is an incredibly complex thing, beast, and what we're really talking about is the angles. The structure of that is so irregular that you get all kinds of different things mixed in. So it's not like a mirror, let's put it that way. It's not like light being reflected off a simple surface like a mirror.
Well, I have a question on this. We see guys with antennas, Yagis in particular, and they'll rotate them, which we know about, but you don't see too much dialogue about them elevating it. And with your chart there, you would think that elevating the Yagi up and down might also be effective.
Well, Yagis actually have quite the vertical.
Oh, I see. Yeah.
Yeah, I can show you something.
Right.
Using EasyNet, you can see that really clearly, that you don't have just one point
Right.
to the horizon. It is quite a dispersion.
It's a big lobe.
And a dipole, for example, is completely like a donut. It's got as much radiation up as it does out. So,
I did some modeling, and the only time you would want to do that is if you lived in my house in Carbondale.
or my house.
And when you're surrounded by mountains that take out 15 degrees, you actually might want to put that lobe up higher.
Yeah.
Or you can achieve much the same by lowering the antenna.
Yeah. Okay, so I guess that doesn't do that. That's interesting. Okay. What is HF terrain assessment? It's basically an evaluation of an antenna's performance given the directivity of an antenna. So its gain pattern is more familiar, but directivity, gain is actually directivity just with efficiency factored in there. But directivity basically says how much does this antenna, does the maximum energy, imagine a sphere around an antenna. If you take a point on that, where's the maximum energy and where's the average, and what's the average energy on that surface? And the directivity is basically the ratio of that maximum point to all the average of that antenna. Okay, then we need required elevation angles for the desired propagation path. And this depends exactly on what it says, the particular circuit you're trying to make a communication with. So if I want to talk to Stuttgart, Germany from here, it's a specific path that will have specific characteristics at any time of the day, during the sunspot cycle, and during a particular month. So you need to know what the angles are statistically for any particular path. Now, things are not specific enough to Stuttgart really, unless you want to use VOCAP to do the analysis. But generally, things like, okay, all the angles going to Europe. When the signals come from Europe to Colorado, what angles do they generally come in on? And we need to know the topographic profile of the local terrain, because that's going to have a huge effect, especially if you live in places like where Ash lives or where I live. Now, if you live in places where, like Phil lives, you have many more benefits, but the profile of the terrain is critically important. So those are the three pieces that we have to pull together to make this whole thing work. And of course, now why do we want to do this? Because we want to know, before we plunk down a bunch of dollars, that a radio, that a particular location is going to be a good QTH, or decide that it's maybe not the most important thing in our lives and we have to sacrifice. But if you're really looking for a QTH to have a really kick-ass radio station, you need to, this is a great tool to be able to do that. And we want to do it so we can find the best configuration for an antenna, for our antennas when we do have that QTH. Okay, and the configuration consists of questions about, okay, how much gain do I really need? If I have a bigger antenna, is it going to make a difference? If I put it in a certain location, is that better than another location? How high should I have my antennas? It is probably the one statement I could make is many times antennas are put too high. And that's particularly true in certain situations, but it is, everybody kind of thinks, well, higher must be better, right? Well, it's not always. It depends on what you're trying to, who you're trying to communicate with, where they're located, et cetera, et cetera. And then, of course, you can have arrays of antennas. You can have stacking as an example. We'll actually show some examples of that later. that are required in some situations. Like I only have one tower and I have one tri-bander on it. Okay, where does that tri-bander go, and how? The tower go, and how tall should the tri-bander be on that tower? Because I have to have one antenna that's got to cover 3 bands, so it's got to be able to get the best characteristics of my location, and also the best characteristics of the height of that antenna, so that it gives me the best compromise. Because 28 megahertz may be very different than 7 megahertz or 14 megahertz. So it really helps to be able to do that. If you only get to have one tower and one antenna, well, maybe you can find kind of the best place overall. And the height of a multiband Yagi, for example, really has to be optimized for all the bands it covers, because the propagation for the 3 bands, for example, on a tri-bander will be very different from any particular location. So, what do we need? We need a model of an antenna's electrical performance. And those that have done modeling know that EasyNet or NEC2, which is the original Fortran program that was written to do antenna modeling quite some time ago, is pretty much the one that's leveraged for all these things like EasyNet. And also HFT A incorporates pieces of NEC to do the actual modeling of the antenna's response. We need 2D profile data. Okay, what's the local topography at a specific azimuth? And we need the elevation angles required for the successful point-to-point communications. And these angles come from the VOACAP, which is a version of IonCAP, which is the Ionospheric Communications and Prediction program that was written by the government a long time ago. And VOACAP took it over because Voice of America, which is what VOA stands for, Voice of America was using it to figure out where do we put antennas to get good coverage into the Soviet Union in those days, right? We want to get a place in Turkey that can really, zap up to Moscow or whatever. So they did a lot of this work and developed a lot of tools. And in fact, if you want to just do sort of routine analysis of propagation, like before a contest, the VOACAP websites are beautiful tools to be able to do propagation analysis for contests. And just Google VOACAP, and you'll see that you'll go to the online site, and we could actually, if we have time, we can give an example of that. But those sites, you can do both point-to-point, you can do area calculations. So if you have a transmitter, you can set your transmitter location and see what the coverage is going to be into Europe, for example, on any particular day with any particular sunspot number and the characteristics of your antennas. It's very, very useful, and it doesn't really allow you to generate a lot of data quickly because it's a web interface. So it's really kind of a onesie twosie, but it's very useful. These tools actually allow you to generate a lot of data, and there are, if you use the VOACAP program itself, you can generate a lot of that data. In fact, all of the elevation data comes from that. And N6BV, Dean Straw, who used to be technical editor, maybe he still is, at ARRL, and he was responsible for most of the recent versions of the antenna book. He wrote HFTA back in the day, and generated all this data from VOACAP to use in the program. So, terrain elevation data. How do we get terrain elevation data? Well, the government has done a lot of work, as you can imagine, taking USGS topo data and putting it on the web so you can actually access it and get it. It's all free. NED, which is National Elevation Database, that's what that stands for. NED data can be obtained from the USGS website, and generally you can, it used to be, and I'll talk about this a little later, but it used to be that you could get sort of random amounts of data. But now that the website has been, the National Map site has been standardized, so it just gives you chunks of data 1 degree on a side. Okay, it's a lot. I can imagine why they did that. It's a whole lot easier accessing their database if they just had all that stuff canned, and you just go say, I need these rectangles of data. Okay, the resolution, you can get different resolutions. 1 arc second, and you'll see this in my demo, is sufficient for what we do. 1/3 arc-second is available if you really want the detail, but it doesn't do anything to improve the accuracy of terrain assessment. There may be other reasons you would want more precise data, like if you want to just see your own location and get more, or get information about some other place in a very detailed way. But 1 arc-second is sufficient for our needs. Multiple formats are available. Arc grid or grid float both work, so you have the option of choosing one. One is floating point and the other is basically integer. So but they have exactly the same data in that, and for the purposes that we're using it, arc grid is perfectly good. They're used. I don't know. I'll get to that in a minute. Let's see if we can do this. Oh, there it did work. Amazing. Okay, so what I'm going to is the national map, viewer.nationalmap.gov/viewer. By the way, all the URLs for these kinds of sites are they're in the back of the slides. I didn't do a handout because I didn't know how many people would want them, but maybe at the end of the meeting, if you want a set of slides, you can, I can email them to you. I don't think they're that big, so you probably, we could do that, or I could get you hard copies. If you maybe let Bob know that you want those, okay? I didn't want to make a bunch of copies and then, oh, we can do it on the blog, whatever. Yeah, if they're available there, that'd be great. Okay, so this is what this thing has gone through a few iterations, and as I'll talk about later with HFTA, the instructions that come with the HFTA program that you can get are really kind of out of date. A lot of this stuff has moved on, so this is the way to do it. I'm just through experience, it's much improved. It's a much easier way to do it than the old process that is given in the HFTA help files. Okay, so you bring the site up and you've got a nice map of the U.S. Basically what you do is you go up here to this download data. You can see that? Yeah. It says in the toolbar up here, you basically say, I want to download data. Actually, I probably should, before I do that, I should zoom into where we want to look, because it's kind of, that'd be a lot of data. So you just double click on this on the map, and you can kind of see where I'm going. Looks like maybe it's Glenwood Springs. Oh, look at that. Okay. So, so here we are, and let's say, okay, maybe we want to look at a particular website. I mean, a particular radio site here. So we'll do download data. And I find the easiest thing is just to use the download by drawing a box around it. Because as I said, since you're looking at chunks of data, you don't have to worry about crossing over boundaries, because the website is smart enough that if you go across, say, the 108 rectangle and the 107 rectangle, like if you pick up all of Carbondale and that part of El Jebel, you'll get both of those rectangles, and it'll actually give them to you in the opportunity to download them. Okay, so you don't have to guess. Just pick the. So I'll draw. I picked that. I'm just going to draw rectangle. It says, okay, what kind of data do you really want? And there's, as you can see, there's lots of stuff here. If you really are interested in barns that are in the valley, you probably can go to structures. But we're picking elevation data. All right, and then we just go down to. Oh, bummer. It just crashed.
That'll teach you to use Internet Explorer.
I know. That's the true with live demos. Let's see if I can get this to go. It doesn't always do that. Let's do that again.
Another creative way to
No,
create.
it's not the data. Okay, elevation.
So if you're looking for your tower site, you just use the whole number degree for the rectangle?
We'll get to that. Yeah. Generally, Google Earth is the way to do it, and you want it to be fairly precise. I mean, we're talking 30 feet. You know, you can get to that kind of precision. This is just going to describe it because I don't want to get hung up on it.
Chart with Chrome.
With Chrome? Then I have to get out of this.
Marathon sauce for you.
Yeah. What was it? Oh, now I don't remember.
Copy it off.
No, it was USGS.
Copy and paste.
National map. There it is. Yeah, there we go. Okay, so this, if you go to just national map viewer, you get this page with all these words on it. What you really want is this link right here. You see that little link? Click here. That's the worst designed website ever. Like, how are you supposed to find that? You know, that's what you want.
That's government logic.
Yeah, that takes you to the viewer site. So let's see if Chrome can handle this any better. Okay. The loading of the website takes a little bit, and I'm on 3G here, so it's not the fastest thing in the world. Okay, here we are. Let's go zooming in now. So, Clark, so what we're really doing here is we know generally where we are. You know, we're somewhere around Glenwood Springs. Like when we're talking about Bob's QTH, we say, okay, I know I'm around Glenwood Springs. I'm just going to take a big chunk of that data. I don't really care exactly where we are yet. We'll get there. Okay. So now we're going to do a download data, and we're going to click to do it by a bounding box. And I'm going to zip around Glenwood Springs. Okay, yeah, and then we're going to go to elevation.
Fingers crossed.
And we pick next. And now it said, okay, you want that kind of data. This is the data that we have. Okay, and here these are USGS NEDs. You see it's north 40, west 108. And remember, so the way it works is west 108 and north 40 is 40 is down to 39. We're somewhere around 39 something right now, so we're below it. So it's going to be, it's the top right northeast corner. So it's 108 to the west, and it's 40 down to 39. Basically, is where we are. Okay. Well, so we don't need the 1/3 arc second. What I want is the 1 arc second, and I'm going to take the grid, arc grid. Okay, so basically I pick that. Now you can get multiple files if you want. Obviously you could pick as many as you want. But I would only just pick that one. I would say next. And now over here on the left you see this nice little checkout thing, right? And now you don't have to pay any money at all. So you've already paid for it,
yes,
basically. So you might as well use it. Right? So what it's going to do is when you go to the checkout, it just asks you for your email address. And then it just says, okay, we'll send it to you. And then maybe 5 minutes later, you get the file in your email. Actually, you don't get the file, you get a link to download it. Okay, and then you get a nice big file that you then can suck into the next step in this process. Let's not do that. Okay, so any questions about what I just did there? It's pretty straightforward if you use Chrome, of course. It's much more stable, but it's pretty straightforward. And again, you can get big chunks of data. They're all 1 degree on the side, and multiple times. If you go, I've done it multiple times, gone across multiple boundaries of these grids, and it just says, oh, you need all of these. So it shows you all of them. Okay. Are we there? Yeah. Okay, so what do you do with this data? For our needs, what we're trying to get done is it would take a lot of manual crunching to do what this program, MicroDem, does for us. Okay, this is a geographical information system program written by Peter Guth, Dr. Peter Guth at the Naval Academy. This program is amazing in what it will do, but it is also probably one of the buggiest pieces of software that I've ever seen. Of course, he charges nothing for it. The government obviously supports it, and so we've already paid for it. But it can be kind of an exercise to get some things done, because being a software engineer for part of my career, I would say, yeah, there's a lot of error trapping that doesn't get done. He just sort of writes it, and if everything goes smoothly, okay, cool. But if it doesn't, oof. But it's incredibly valuable and incredibly powerful. It takes GIS topographic data like we just downloaded, and for our needs, it generates 2D terrain profiles. These are basically just vertical terrain profiles at one azimuth. Now, you can imagine if I wanted to do this every 5 degrees for my location, and I have a topo map, you could sit down with a ruler and you could go out, you know, for, what we're trying to do is go out about 3 miles, okay? 4,400 meters is what we usually use in HFTA. So you'd have to do every point, if you want every 30 feet on that profile, it would take you a long time. Then you got to do the next one and the next one. Okay, so you can see it's a lot of work. But what this program does is basically automates that process. So the profiles that we generate with microdem are then used by high-frequency terrain analysis, the program, to analyze the reflective and diffractive effects on propagation. We do 5-degree increments. The range is 4,400 meters, and the horizontal resolution is 30. Now it can do all kinds of other things, but HFTA only really understands those parameters. So those are what you need to make microdem generate for the purposes of terrain analysis.
Just going back a second, you talked about a 1 second arc.
Yeah.
Could you explain what that is?
The resolution of the terrain data is 1 arc second. Okay, so it's one second of step. Okay,
yes. The second being
well, degrees, minutes, seconds, right? Yeah,
60th of a degree.
Right. Okay. So and 1 arc second is more than adequate for us for our needs.
The HFTA program only uses 5 degrees, so you've got data that the program isn't able to deal with.
Yeah, I mean, they actually use the 30 meters for 100 feet. We've got plenty of, 1 arc second is more than adequate for 100 meter steps.
How many feet is an arc?
I mean, 100-foot steps. What's that?
At this location, how many feet is involved in an arc second? I know it differs from latitude to longitude.
Yeah.
It depends the distance from the center point.
Yeah, 1 arc, yeah, I don't know.
Center point of the Earth?
I couldn't do that.
No, your antenna's at a center point, and it's measuring 360 degrees around your antenna when it's putting out.
Oh, I see, okay.
And the arc second data is what are the various things you're hitting in the course of getting out.
That's in a horizontal plane, is it?
Yeah, it's just the terrain profiles are done at 30-meter increments. That's more than an arc second. I can't remember what the number is. It's a good question, but I probably would get it wrong if I tried to calculate it in my head. But you just need better than 30. I mean, you really would like to have 15 or 10 meters as the resolution to give more or less good sampling that would give you a reasonably accurate profile. Okay. And we're not talking, things are in this effort are not very precise. So being overly precise is just really it's unwise, and you're just fooling, making stuff up. It's not really going to give you any information. Okay, so let's see what we can do with. Yes, I know that's. Thank you very much, Microsoft. Okay, microdem. Microdem is available from the U.S. Naval Academy. There's a website, the URL's in the back of the slides, and there's different versions. It's kind of confusing. I would suggest that anybody who wants to do it and has any kind of questions about it, come email me. And I'd be happy to give you any help I can. Basically, I've moved, there's a 64-bit version which is fairly recent, and it seems to work best. I think that's probably where all of his effort is going in terms of fixing bugs or making it new features or whatever. He's very actively involved with this program. You can get to him on forums, and it's amazing. He'll answer questions almost in the middle of the night about this stuff. It's like, whoa. Because I had some problems with an earlier version, and he was very helpful. So go to their website, and the 64-bit version, I think, is the most recent. It's the one you really want to use if you have a 64-bit machine. Otherwise, you use the 32-bit. This first splash screen comes up. You just basically need to dismiss it. This program, as I said, is incredibly powerful, but it means it has an options dialog that, is like, holy smokes. How am I supposed to know how many options? Okay, so in the HFTA documentation, there is a bit of a discussion about how to set these options. And I'm going to go through it here, and in the notes that are on these slides, there is descriptions of how to set these options as well. Again, if you have any questions, if you want to do this and you have any questions, just email me. But there are a few of the options, only a few, fortunately, that we really need to worry about. We need to go to the views, okay, and this is where you'll see an interesting name, weapons fans. So that should give you a clue what this program was originally written for. Okay, it's originally written for gunnery, so that you could figure out, given terrain, what your line of sight is and what angles you needed to get to set to get to a particular location in a distance. Ambush, I'm not sure quite if that's useful to hams or not. The one that's important to us here is called the LOS fan algorithms. Now, a fan is basically, as you would imagine, a fan. It's sort of like, okay, we're going to take all, we want all the trains for this whole fan. In our case, we like 360. Okay, but then I suppose in a certain situations you might only want 25 degrees or whatever. But you need to configure this so it generates, this is where you configure it to generate the right data for HFTA. I don't expect you to memorize all this, but the important thing is, for example, radial lines, this first fan drawing method, I think the default is point-to-point. You want radial lines discrete. You want to be, and that causes this dialog to become active over here. You see my, yeah, okay. And the ray spacing needs to be 5. That's the 5-degree increments, okay? Then you go down here to this point selection method. I think it's scaled radial settings is the default. You want to have constant radial spacing. That enables this dialog over here, and you want 30. That's where we get our 30 increments of 30 meters, okay? Everything in this program is meters, and it's best to leave it in meters. There are places where you can change it to feet, but you don't want to do that. Just leave it in meters, think in meters. Okay, so those are the, in this particular dialog, these are the two most important things to get right. Is 5-degree spacing and 30-meter space, point spacing of 30 meters, ray spacing of 5. Weapons fans, you can set what are called range circles, and we'll show those in a little bit, but this is where you actually set those. And this button here actually takes you to that same dialog. So there's a lot of kind of spaghetti in here where you can go from one dialog to another dialog, but you can also get to that dialog from another place. But I tend to use this options dialog the most. Okay, so the other place you want to go to is units. The units, we want to have decimal degrees. We want to have distances in metric. We want to have elevations in meters and azimuth angles in decimal degrees. That's the easiest to use. And if you use Google Earth to get your coordinates, you can change it to decimal degrees, and it makes it much easier to follow through. And I'll show you how to do that. We also want to look at the coordinates here. And this is just more operational stuff. We want verify graphical selections to reasonable and verify keyboard entry, because we're going to be going to points in this on this terrain, and we want it to give us the option to say what point do you really want. Okay? It's too hard to do it just with your mouse. And I think that's all we're going to just go over there. I just wanted to go through those because this dialog can look awfully forbidding, and it's not really that complicated once you know just a few things you need to change. Okay, so once you've got dem up, what you need to do is then you have to say, I want to open a dem. That's the first step, okay? And in this case, we're going to use a version of the North 40 West 108 that was floating point. This is grid float, okay, instead of arc grid. But again, I've done them both ways just to compare them, and they're identical. When you look in microdem and the data you get out of HFTA makes no difference. And they're actually about the same size, so I don't know. There's some other reasons you might want to choose floating point over integer, but it's not needed for us. So we pick the float. It reads it in. Blammo. Does it look familiar? Sort of. Okay. This is again the whole chunk of North 40 West 108. So here's Carbondale right down here. Here's Glenwood Springs. Here's Silk. So with this one rectangle of data, we can cover a lot of club members' locations. Aspen is in 107, so from up about Basalt, Elgeville up, I have to use 107 to get to me. But for most everybody else, this covers a lot of terrain. Okay, so we have this. What do we do with it? Okay. Well, now we go back to, we have to say now, as Clark was very clearly said, well, we need exactly that point. So what we're going to do is we go to Google Earth, good old Google Earth. I don't know what we did without Google Earth. It's like with Amazon. It's Amazon and Google Earth going to rule the world. But let's say we were, well, let's just, for grins, let's go to Clement Springs and let's go find Bob's house. Okay, I think Bob's house is over here somewhere, isn't it? Yeah, I think
somewhere
it's
up the hill.
here. I think it's like right there, isn't it?
That's it.
Okay. So, and I think this is your antenna
You
right
cut your
back
grass,
here. Is that your
Bob.
tower right up there?
Maybe Google Earth shows you wires.
Yeah. Isn't that your antenna? Your tower's right in the back.
Insulators on your wires.
Okay. So here we have, now, unfortunately, I just realized, this Google Earth, I do most of my work on my desktop PC where I do have Google Earth configured correctly. Here I don't. Here I have, you see down here on these coordinates down at the bottom,
Yeah.
this is in degrees, minutes, seconds. This is not very helpful unless you like to do a lot of divisions by 60. Okay, so what you want to do is you go into the Google Earth configuration, change it to decimal degrees. That's all you have to do. Then the numbers will be nice and handy and just what you need. But so basically we find out where that location is. And we want to put, that's the location we want to use for microdem to tell us, to generate the terrain data from that point. Okay, so that's so much for Google Earth's utility. So let's, we're going to do the same sort of thing. Actually, I happen to have Bob's, this is my cheat sheet. I happen to have Bob's terrain, so what I'm going to do is, I'm going to say, you can see there's all kinds of buttons up here that do all kinds of things. And you can generate all kinds of overlays, calculate all kinds of things. You can do cartography, just there's a ton of stuff you can do with this program. Some of it's fun, some of it crashes, but it generally does what we need it to do for HFTA, fairly straightforward. So what I'm going to do is, I'm going to first, I'm going to kind of zoom in. This little thing is subset and zoom. Does that show up? Yes. Okay, this little icon. It takes a little while playing around with this to get it right, but generally we'll make it a little bit easier to see what we're doing. Okay. So we know that, as I recall, Bob's QTH is right around over here somewhere. Okay. So what I'm going to do is I'm going to do a nice little feature called calculate, which is so obvious where it is on the keyboard. Okay. Now, I'm going to go to see Bob's house is at 39,563,321. 563,321. And 107,335,090. I'm just asking it, where is this point? Because I can't really, no, I don't want to, it always asks you for another location and say, no, I don't want another location. So you can see right there, you see the red rectangle? That's Bob's house. Okay, that's his tower, actually, not his house. Hopefully it's on where his tower is. And the one problem with this little thing is that if I then zoom in on that, that rectangle disappears. So it's kind of like, wow. Be nice, but generally it gives you the right idea. But we're not going to get the location into microdem for its use by using the graphical. We use that keyboard feature. Remember, I set that option to keyboard. Okay, so what I'm going to do is I'm going to say, all right, I want you to generate a weapons fan, and I'm going to just double click more or less than that. This doesn't have to be accurate. Okay. Now, unfortunately, I have to enter that same number, pretty close, 563,321 and 335,090. So I got pretty close just with the mouse. But now what this is going to do is it's going to take that point and use that as the center of the weapons fan or terrain data that it's going to generate. Okay? And I say, okay, but now it's asking me, okay, number one, what do you want to call this thing? So when we generate all these files, you can recognize that you just did that. If you don't put anything there, it gives you some bizarre thing like S dash some number, okay? And that's okay if you know what it was going to do, but it doesn't tell you that that's the name. So if you do it multiple times into the same directory, and this always goes into the same directory, you know, it'd be a big mess. So I like to do things like, say,
12 gauge.
K9 MWM dash home, something like that. I don't know. When he gets his remote location, then he'll be able to differentiate. Okay, there's a couple of things that need to be changed. When you first open this dialog running microdem for the first time, you want to set the max range to 4,400 meters. Okay. Now that again, that's because HFTA uses that number, and the number of samples that you take at 30-meter intervals need to fit it. You know, HFTA is trying to. It expects a certain size file with a certain number of samples in it, and it doesn't want to see anything more. If you do more, it'll give you, it just crashes. Okay, so you want to use 4,400 meters there. You want your right boundary to be 355, not 360. It originally comes up to 360. I don't know. I haven't actually tried it recently. What it does when you leave it at 360, but you want to make that 355. One important thing to make sure is that save radials is actually checked. Now this won't be active if you haven't set the option correctly, okay? So if you see this is not, you can't check it, then that means you didn't set the options right, okay? It's pretty nice. All right, so we're going to go ahead and generate some data. It's done. And now you can see, it's a little bit hard to see here maybe, but I'm going to zoom in a little bit to try to make it easier to see. Okay. This is 4,400 meters from Bob's house. Okay. And these are the radials of line of sight where he can actually see. Okay. Whereas up on this side, he bumps up against the flat tops pretty quick, right? And he's right here in the middle of that. But so you can see he bangs into all the ridges around here. You can see pretty well out to 4,400 meters down the valley and down toward Grand Junction in that direction. Okay, but that's basically what microdem does. And if you were trying to set up a cannon, I suppose that would help. But from the point of radio, this is wonderful because it generated all these radials for us in just a few seconds. Okay, and now
each one's 5 degrees.
Which everyone is, no, it's 5-degree increments. Okay, I mean, if you want to know which one is, this looks like this one's due south, right here.
Yeah.
And there's due north is probably right up there along with.
Can you actually tell elevation
What do you mean?
of the profile around?
Yeah, that's what the profile. That's what the profiles do. Is that you'll see
That's
that.
coming.
Yeah. Actually.
Because I was thinking about satellite operating stuff.
Right. Let's do something now. This is totally. Your.
Don't crash.
Yeah, I know. Can't help it.
Let's do something confusing.
Okay. I'm picking what's called LOS, which is line of sight. Okay, which is going to give us a line of sight profile. And it's totally random. I just picked the point, looked like it was close to your house. Okay, and then I'm going to pick some. You see that guy? Okay, where would you like to pick a line of sight to? Up under the flat tops?
How about the flat tops?
Moscow.
Okay. There. Basically, everywhere that's red is you don't see.
You're right.
Now,
See anything?
Not much.
This doesn't look like it's formatted properly, and the vertical scale is all goofy. But this gives you an idea what you can do. The kind of thing you can do with this program is you can say, "Oh, I want to know what the line of sight is over that direction," or whatever. But that will show you the black areas are what you see, okay, and the red ones are the ones you don't. Okay. Now, that's not that gives you a better view right there, okay. And of course, so if you're running VHF or something like that, it might be really important. HF probably would peek over, you might not, because it's gonna diffract over the top of it.
So the green you can see there, but the
Yeah.
red is blocked?
The green is his line of sight. That first little red patch is probably where it goes down into the canyon. You can't see down into the canyon. And then it comes back up the other side. Oh, and there you can see it, and then it goes probably over a bump, and then back up again, and then behind it. So. Anyway, so again, this program is wonderful. If you're really interested in geographic information systems, man, play on. You can overlay all of the roads and the bridges and all that kind of stuff too, but we won't get into that today. Okay, so we've done this. What's the result of this? Well, the result of this is if we go to terrain, here we are. Okay, I have a little favorite that takes me to the terrain files, and this is where it generated all those files. Okay, and it's 0, 5, 10, 15, etc., all the way to 355. Okay. Now let's see what's next. Let's get out of here. We have our geographic data, and we have our terrain profiles. Okay. Now what do we need to do? Well, HFTA, the High Frequency Terrain Assessment, as I said, was written by Dean Straub at ARRL, and is only available in the antenna. It is not available anywhere for download from any site. And I'm not sure if this is ARRL's perspective or whether Dean just felt like this is the way he wanted to get it distributed. Anyway, it's available in the 19th edition and later. I have the 21st edition, which is just a couple of years old. I don't know if there's still development being done or bug fixes or anything. It's the version I have seems to be the one that I see in all of his presentations. Oh, by the way, there are a couple of presentations on HFTA by Dean Straub that are, the URLs are in the notes. And they're very worthwhile listening to those. You get a lot. He probably says all the things that I'm going to say wrong. He says them right. So anyway, but he's the guru. He really knows what's going on. Okay, HFTA it's an enhanced version of NEC2. That is the antenna modeling software that understands diffraction. Okay, that's the one thing that NEC doesn't handle. NEC is designed to be only flat terrain. Okay, it really provides wonderful, an easy neck as well. Provides great antenna modeling and results that, but they only reflect the assumption that you're in Kansas. Okay, and they don't work at all when you have mountains like we do. Okay, we have the need for diffraction around here in spades. Okay, so HFTA analyzes the effects of antenna height, antenna position, type, but only dipole and Yagi types are supported. Now, HFTA had an earlier life as a DOS program called YT, Yagi Terrain, that Dean wrote back in the 90s probably or something like that. And then he just brought it forward into Windows and enhanced it a little bit, but it only understands dipoles and Yagi. So verticals, if you want to get into verticals, it's not going to help you. But in a place like this where we have a lot of terrain, verticals don't really play that well anyway, so maybe it's not such a big disadvantage. And it also addresses the concept of stacked antennas and what you can do with stacks. And of course it takes into account ground connectivity, which NEC does as well. But these are basically all the switches that you have in HFTA. Okay, so HFTA takes the terrain profile data to analyze the reflection and diffraction of HF signals, and it generates a gain versus elevation graph for that antenna. So just to show you what these look like, here's an example terrain profile. I don't remember where this was. Oh, this is for KQ0C at 40 degrees. Okay, and this is your remote, not here. And it starts at 2122, and 30 meters later is 2111, and then 60 meters is 2096, and this is the cliff that you fall off of at his house. Okay, so this is the kind of thing that this is what it generates. Microdem generates basically this kind of a file that HFTA then uses. Okay, and the addition to HFTA that was not in NEC is this concept of ray tracing to analyze the 2D terrain effect on antenna response. And I'm just going to give a quick overview of what ray tracing really is talking about. You're basically looking for positive and negative interference, destructive interference. You have two ways of really doing that. One way, and basically that's what you have two multipath to your antenna. So you have direct signals and you have signals that are reflected, and they come together and they either add or they subtract from each other, depending on what the phase is. Okay, and so the path, everything is, and the distance and all that is going to have a huge impact. And it's, for example, multipath, which is real common in VHF. If you're in a city and you've got reflections coming out of buildings all over the place, you might walk in, your cell phone might work in one location, you go 10 feet down, it doesn't work anymore. So what happened? It's just basically where you are in that pattern of interference. Okay, and so reflection is this is the direct wave coming in. You've got a reflected wave coming off the terrain. And then diffraction, which is the big addition for HFTA, is that you have direct signals, and then you have diffracted signals which get bent over the terrain. Okay? And that makes, if you live in a place like Aspen, for example, the only hope I have of hearing anything below my direct line of sight is that some of those signals come in and get bent down, especially on signals where the wavelength is similar to the size of the obstruction. Which is also works the other way around, is that if you're transmitting and you've got this big obstruction, it's going to diffract all of your signals. So your signal strength is going to get really impacted further down the path. Okay?
Is that similar to like knife edge effect?
Yeah, it's exactly that. Yeah. It's the reason why you can put two hand figures together and correct your vision, or you can look out the top of your eyelid, which has got a knife edge basically, and you can now see better because it has an impact on all the different rays of light coming from whatever you're looking at. Okay, so it uses ray tracing then to analyze that effect, and when you take statistical elevation data, it calculates what's called a figure of merit. All right? And this is a very it's sort of a average number that gives you a sense of how well your antenna installation is going to work. Okay? And elevation files, and these are what VOA cap or ion cap are used to generate. Okay? And these ARRL has generated, Dean Straw himself, in fact, generated all the data you'll find in the files that come with HFTA. Those angle files are there, but they are very general in that they only apply really to Colorado to Europe. Well, that's kind of a general thing, right? But you can take those, take vocap and generate exact propagation predictions and get angles for your particular location and terrain, which is very powerful. So the elevation data files are just going to show you an example. This is what they look like. Basically for elevation from 1 to 33 degrees, for 80 meters, 40 meters, 30 meters. Now what these numbers mean is these are the percentage of the time that this angle, that the signals come in at, say, 1 degree. So on 20 meters, 15.3% of the time from Denver to the Far East, this is Japan, okay? The 1 degree angle is 13% of the time. And you can see that Japan paths are almost exclusively very low angle. Okay? You get up here into the 20 degrees, the very above 14 degrees is almost nothing. Okay? And again, these are statistical averages. They apply to all the complete solar cycle, all months, all times of the day. So again, that's why we don't have a lot of precision here. We just have a general sense of what's going on, but it's still very valuable because without it you wouldn't have any judgment at all. But they are very general. And again, with vocap, you can, or make VOA it's called, that comes with HFTA. And then you can use that with VOA area to actually generate graphs of what your transmitter would do into Europe, for example, or how well you would hear, what you would expect the angles to be coming from Europe. to your particular location. Now, yeah, so I'll leave it at that. One nice thing that HFTA does is generate this out.prn file, and that is basically an analysis of your antenna for a particular frequency and at a particular, what would you describe that to be, a particular azimuth, what the antenna was, and it gives you elevation versus gain data. Okay, so you can take this data and feed it into VOA cap eventually to generate a accurate response for your antenna, and given all these, how well these angles match up with what VOA cap thinks the angles will be from that whatever you're trying to communicate with. Is that clear? Basically, this is a way of customizing HFTA to give you angle estimates that are much more accurate than just the general ones that you are provided for you.
Can you do any of that by frequency or not? Or is that?
Yeah, this is actually 14 megahertz.
Okay.
Yeah, now you could do one for any frequency you want. Yeah. But HFTA only understands the amateur bands. So okay. Now, what can we change in HFTA? How much time we have to do? I'm not going to spend a lot of time at the minute with this. Basically, this is HFTA, okay? The first thing to do, of course, is to pull up the help file and go, how in the world do I use this? Is it going to crash? There it is. Okay, you can see this was written, oh, get out of my face. This was written in 2007, so obviously it's almost 8 years old now. And I don't think it's been updated. A lot of the stuff that's in here about how to prepare, you know, as you might have seen, that there's a lot of effort goes into getting the data, right? So a lot of this help file is about using whatever resources are available. And a lot of this stuff, as I said, is out of date. But it does provide information about how to set the various fan drawing method, for example, is here. Even though the dialogue is no longer, it doesn't look like this anymore. So you kind of have to take it all with a grain of salt. If you follow what I did, it should be much easier. Anyway, so this is the help file. It's good to look at. There's some good stuff in there, but realize that a lot of it's out of date. HFTA units, feet, meters. When I get to HFTA, it's easier for me to think in feet, so I change it to feet, right? And I want diffraction on. You can turn diffraction off, and you'll see that it has some effect. Some paths are going to be much more affected by diffraction than others. If it's a flat, if you're in Kansas, there's no diffraction really. It's just reflection off the ground where you get ground gain. But if you're in here, yeah, and I have a really sharp edge I'm trying to get over, well then diffraction is going to be really important. And there's an option here to move a tower back. So, say you have a really steep drop off and you want to know, well, do I want to put the tower right on the edge or do I want to put it a little further back or whatever? Then this is an easy way because it basically takes your terrain profile for that azimuth and then just adds a number to it. Okay, usually 30 feet or something like that. So it's easy, an easy way to explore that. And then of course you have your soil types. Colorado, we're somewhere down here in the very poor soil to poor soil. You know, it's not. You can pick any one of those. It probably doesn't matter which one. I generally go with just 213. Okay, so those are the options. You have frequency. You just type the frequency in here you want. So if you want to do 40 meters, you just type 7.1 or 7.3 or whatever you want to look at. And then you have the terrain files, antenna types, and the heights. Okay, and oh, I didn't want to do that. When you click that, it takes you to wherever you've looked at profiles before, and you can select whatever profile you want. Now this dialog is nice. It looks like a pain, but actually it's very nice because if you select cancel in that previous dialog, then it says, well, do you want to just clear this whole line completely? And that's a nice way to say, yeah, I just want to get rid of all the data in that thing. I don't want to, I had 4 in there, but now I only want to look at 1 or something like that. So you can just click on that profile, say cancel, and say, oh no, I don't want to clear it. I want those 3. Now it turns out you need to have 1 and 1, but that's okay. So these are the profiles. So if you want to explore different angles, for example, you would set different profiles here. One at 40 maybe, one at 160, whatever you want to do. Then you have antenna types. So when you click, you get two different dialogues. Well, when you click over here, you go to the profile file. So I would just click KQ0C15 for bands. Okay. But if you click in this area, either any of these areas over here, you get this dialog, which allows you to select an antenna. And as you see, it's only dipole, 2 element, 3, 4, 5, 6, 8 elements. Wow, 8 elements on 14 megahertz, that'd be pretty cool. Or dipole.
So these are generic antennas
Yeah.
that they've programmed in there for the gain and
Right,
everything?
yeah. These are, so that's why the elevation angles that you can generate from the output file, this out.prn, are nice because you can really change the electrical model that it uses. Okay, so another nice feature is, well, you have these, you can have a stack of 4. It supports a stack of 4. And you just, a stack of dipoles, that doesn't really work too well. Just change this back to, say, 3 element. And I could put one at 40 feet, something like that. Okay? Nice feature too is this copy business. If I do save copy, it changes these buttons to true. So I can say, oh, I want to copy that to there. I want to have the same antennas and stacks, but I have different profiles, for example. Anyway, there's a lot of flexibility in this dialog. And I'm just going to cancel it. You can plot the terrains. And you can choose which terrains you want to plot. If you don't want to, you just want to look at one, or you want to look at all 4 of them, you want to compare them. So these are, let's look at these. So it says you have KQ0C at 15 degrees, N0K at 40, KQ0C at 40, and a KQ0C at 40, but I was looking at 2 different heights of antennas before. But it doesn't affect the terrain. The terrain is obviously at 40 degrees the same. Okay.
Well, wait a second. Let's just say I'm Ashton for a minute here, and I've got this big old Mosley antenna on top of this big old tower that goes up and down. It would seem like the question you want to have answered is, at this particular frequency, where do I want the height of the antenna most of the time? Does it tell us that?
You can do that. Yeah, we'll get to that. I think I can answer it.
What?
Take your time.
Oh,
No.
Try it and find out.
Does anybody have to leave at noon? 12:30? 1 o'clock? 12:15. Okay, I try to. So I just want to make sure we understand all the controls here because they are important. And so this is, okay, so, no, I don't want to do that. So you have the profiles, you have the antennas, electrical characteristics, and the third piece was the elevation file that we looked at, right? That gives you the angles for any particular area, what they look like. And that's what you choose here. So right here I have W0COEU. And so let's see if I have that, where are those files going? I think they're under HFT A. Yeah, so here they are. So you see the ones you get with the antenna book are W0A, are all the US ones, okay? It's possible to get the worldwide elevation files. But I can't remember where I got them from, so I have to look into that. But anyway, so these are the ones, obviously, they're just the 7 or so that are here for Colorado, to Africa, to Asia, Europe, Japan, Oceania, South America, and the US. Okay? And we'll look at some of those in a minute to see what they actually look like graphically. It's quite interesting, the difference. But this is, so you can pick any one you want. If you're in Iowa, you pick, whatever. Okay? And it gives me the option to then clear it, because sometimes you want to show antenna responses, but you don't really care about the statistics because it doesn't make any sense. Because it's always, you can only have one zone of the world as your elevation statistics at a time. So I don't want to clear that. Okay, and then you want to choose maximum elevation angle. Generally, I just leave this at 34. And the other thing you want to do then is say, compute. And there is you've got Ash's 15 degrees, you've got Phil's 40 degrees, Ash's 40, and again Ash's 40, but at different height. And this is the kind of thing you see. And this is, again, for Colorado to EU. Now, 15 makes no sense. Well, probably not, but for some reason, maybe his antenna is stuck at 15 degrees, and he wants to know, am I going to hear anything? So,
Scandinavia.
is there a question?
No, that's
Oh,
Scandinavia.
Yeah, I know. It is part of Europe, I guess. The important thing to see here, and I want to just spend a minute to go through what this is telling us. Okay, this axis here is gain in dBi, which is over isotropic. Okay, so a dipole is sitting right around 7 dBi. Okay, so this response in here is kind of like a dipole. I mean, so you know, these antennas are basically acting like dipoles at very high angles, because they don't have any gain up there, right? The pattern, these are 5-element, 4-element. They have a very tight beam pattern, right? So their response to an angle, to a signal coming in at 31 degrees is kind of like, well, it's a wire, you know. It basically jumps over all of these nice elements you have sticking out there, and the driven element is basically a dipole, is what this is really telling you. So the gain is on the left here, and angles on the bottom, and on the right side you have elevation statistics percentage. So what HFTA does beautifully is to take your antenna response and overlay it upon these bar graph of angles. Okay, and these angles, you can see what it's basically saying is, okay, 3% of the time the signals come in at an angle of 16 degrees. And there's a nice little pop-up that sometimes comes up. So basically, it's at 16 degrees, you have 3% of the time. So if you cover that angle very well, I mean, it looks like everybody has a fair amount of gain. Phil has about almost 16 dBi of gain there, okay? And that's because his terrain at this particular angle is more or less looks like flat to the antenna, because for the first 100 meters, 100 feet or so, it's really kind of flat. Okay, it doesn't change that much. So his antenna.
How many Yagi is this? Or?
It's over here. So which one are you talking about?
Okay.
It's a 5 out. This is his his KT36, sitting at where it is on the corner of his property.
Okay.
But his angle to Europe is kind of back into that saddle, so it doesn't look like it doesn't change that. It's not the fall off. If you were to go south from there on a 60 or 70 degrees, he goes off the cliff there.
Right,
so
right.
It's very different, yeah. And we'll show some of his profiles to compare. But anyway, the important thing here is not to look at the data so much as to just see that this is the data that that HFTA presents with. Gives you gain dBi on the left, the angles on the bottom, and the elevation statistics on the right. The bar graph is the elevation statistics. Basically, it's just a sort of average percentage of the time. Again, it's over a whole cycle of the solar cycle, for every month, for all times of day. Okay, so it's a very general measure, but it generally gives you a sense of, okay, signals that come in from Europe into this area are generally below 20 degrees, and there's nothing any higher. So if your antenna, sort of like mine, only sees 40 degrees, you're just not going to hear anything, right? So, okay, let's close this. Go back to the presentation. Okay, now we did that. What we're going to do now, real quick, is we're going to just go through some examples, and we're going to look at what flat QTH, kind of look at how things change for a flat QTH, things like antenna height, antenna type. What does the response look like in HFTA? And then we're going to look at my QTH. Okay, we're going to look at the height, the operating frequency, URT versus JA, figure of merit. And, I didn't really talk enough about the figure of merit. I'll do that again in a minute. And we're going to compare myself to N0KE to Europe, which will be a defeatist thing to do. And then we're going to give some examples of N0KE, KQ0C, and K0ALT's QTHs. Okay, well, this is good. This I left it till here. This gives you a sense of Colorado to the U.S. and Colorado to Japan. Look at the difference in the angles. Okay, this is why I can participate in things like NAQP or sweepstakes, the contests that sort of address the U.S. I can hear things. I can do pretty well. But just for information, my antenna installations basically don't see anything below 12 degrees. So you can see that in the case of Colorado, below 12 degrees, well, I see a fair percentage, probably maybe 40% of the signals come in at angles that my antenna should respond to. Whereas if you go to 12 here, no wonder I don't hear Japan very well. Okay, even though my antenna to Japan actually responds better. Okay, but to Europe, because I got Red Mountain in the way, it
How do they get the average for Colorado? I mean, how do they figure that, from the center of the state or from?
yeah, see, that's exactly the problem. It was done by using VOA on a computer. And basically, Dean just wrote some software that would just crunch through all of the locations in the world, giving general. He probably picked Denver as an example.
So it's not really relevant to
No,
what we have.
it gives you a general sense because
It's what it would
100
be
miles
if
to our
it-
east, the angles are still pretty much the same.
Well, if we had flat ground here, we
Well-
had the same thing they do.
No, but that's what the terrain gives you. Okay,
Right, but they're
the
not-
angles are the same.
Right, but that's just a general overview,
Yeah.
like we were on flat ground.
Right, and also it's the whole solar cycle, every
Yeah.
month, every time of day, so it's a very general measure, but it still has merit. Okay, and the other thing I wanted to get out of this is the figure of merit. What this number, the figure of merit right here, you see it says 5.3. Okay? That basically is a weighted average of the gain at any particular angle times the percentage of time that angle is valid, if you will. Okay, so you just take the numbers of the gain as you go around this curve and multiply them times the percentage of the time that that angle is active, and you add that all up, divide by the number of samples, you get the average. Okay, so a figure of merit is a very general number. So this basically says for a dipole at 60 feet on flat terrain in Kansas, okay, has a figure of merit of 5.3. Now, relative figures of merit make sense. I mean, you can get, if one figure of merit is 10 and another is 5, that means you get a 5 dB difference. But the number itself absolutely doesn't really mean a lot. Okay, so you shouldn't dwell on, oh, I'm only at 7.2. That's not an absolute number that makes any sense, really. But the relative figure of merit is very important. Okay, go back here. All right. Oop, I put that in there. Okay, here's for flat terrain again. We're just going to look at the difference between a Yagi and a dipole. A 3-element Yagi at 60 feet, a dipole at 60 feet, flat terrain. The 3-element Yagi has about a 5 dB gain. And the figure of merit is about 5, an increase of 5.
You still going to Japan on that one?
This really doesn't matter. Yeah, I just left it here. This is Europe. This is Europe.
Okay.
You can see down here. You can see down here in the elevation statistics says Colorado EU. Okay, so this is just very general. You know, it says okay, a Yagi is about 5 dB a gain, and that's dB, not dBi, because now we're doing a relative number. Okay, so. This is just to give you a sense that HFTA does a pretty good job of doing the same thing from a modeling perspective as EasyNet. These are the heights. I've taken the flat terrain and a 3-element Yagi at 0.5, 1, 1.5, and 2 wavelengths high, okay, and giving you the angle of the maximum gain. The angles are, especially toward the higher heights, it does a better job. Now, this may be because HFTA is playing some terrain business that NEC doesn't do, and I don't know whether it's a failure of the algorithm or it's an improvement. But anyway, it's a little different. But generally, you see that they correspond very well. So it gives you a confidence that HFTA is doing the same thing that EasyNet would do, which is pretty trusted. And the figure of merit, as you can see, moves from just a 4 at a half a wavelength high up to around 10.2 at 1.5, and doesn't do much to go to 2 wavelengths really. And on this graph on the right, you see you have a half a wavelength high is really kind of just a broad, and its maximum gain is around 28 degrees because it's pretty low. And we're talking again at 14 megahertz, it's 20 meters. So the angles are pushed up. Now, as you move up in height, you can see we go to 1.5 wavelengths, to 1 wavelength, then to 1.5 wavelengths, and 2 wavelengths. Basically, the takeaway is that as the antenna is raised, the main lobe moves lower. Okay, So as you take that antenna up, the main lobe of radiation lobe moves down. And since generally, most paths you're trying to access are with elevation statistics which are pretty low. I mean, predominantly, worldwide, predominantly where you're trying to get to, the angles are going to be very low. The US and our local kind of environment is the one exception to that, really. Okay, here's the effect of terrain on my QTH toward Europe. And you say, sucks. The Red Mountain the cutoff here you see is because of Red Mountain. And basically takes my, now remember, this is dBi gain over here, so my antenna should be up here, all right, when it gets to its ideal elevation angles. And higher angles, it does seem to sort of follow that. All these oops, I didn't want to do that. All of these, this noise here really is from diffraction effects, and you shouldn't put too much credence in that. Don't worry about it. They don't always make sense, and so it's difficult. You don't want to focus too closely on things like that. It's the general sense of what the data is telling you that's important. But so what it's telling me is that basically at above about 18 or so degrees, my antenna does kind of work like a dipole, you know. But below that, because of the terrain, I only hear a very small percentage of the signals. And the figure of merit for my antenna is minus 5.1 dBi, okay? Which basically says take a dipole and bury it. You know? So no wonder I don't hear Europe very well. Most of the signals, you know, at least 85% of the signals come in at angles that I'm never going to hear. And here's my profile. You can see the difference between flat, which is down here in blue, and my terrain, which starts at about 7,900 or so and goes up to about 10,000. Now this, you know, this doesn't look like it's very steep, but it changes, fundamentally changes. The angle from here, the line of sight is 12 degrees. And that makes a big difference when all those angles, when most of those signals are coming in below 10 degrees.
Sucks.
All right, so would it help to raise my dipole? I don't know. So this is something you can do. You can say, okay, well, let's take it from 30 feet to 60 feet. And it's always a good idea to use a flat terrain as a reference, because oftentimes you can't, otherwise you don't really get a sense of where you are in propagation. But a flat terrain with a dipole or the same antenna makes a lot of sense as a reference. So you can see the Aspen's at 60 feet, and here's 30 feet, and 60 feet does some gyrations here because the dipole is a little higher, but primarily the gain that I gain over here is taken away from over here, which is not necessarily bad, except I still got my 12-degree cutoff and doesn't help me. So raising a dipole, I might get a little more, like the figure of merit goes up about 3 dB, so maybe I get a half an S unit of improvement if I put it up a little higher, but it's only affecting these signals that are way up here, which is a very small percentage of the time. Okay, here's the effect of operating frequency. Does 28 megahertz look better than 14 megahertz? And yeah, it does a little bit, but I still have my cutoff. But I do get better gain at 28, on 10 meters, even though now there's even, seems like probably fewer signals that come in, because as the frequency goes up, bending in the atmosphere, in the ionosphere is less, so the angles actually fall as you go up in frequency. So that counteracts the effect of getting any increased pattern benefit. Okay, Europe versus Japan's elevation statistics are pushed way to the low angles as we might expect, and my 12-degree here in going toward Europe is actually now quite a bit better because of the I'm looking down the valley. But I also have Pilot Butte in the way, and I think that's about where this, I think I'm getting some effects, diffraction effects off Pilot Butte, which is what causes this dip here at 6 degrees before it regains sort of the dipole shape. The figure of merit's only 3.5 dB better, but I cover a lot more signals. So when the conditions are good, I should be able to hear a lot better than I do toward Europe. Okay? So even though the figure of merit says, well, your gain is still not very good, but remember, those elevation statistics and this gain are really dependent on conditions, propagation conditions. Okay, and now here's myself compared to Phil toward Europe, and Phil's maximum gain, and this is his KT30. I always want to get the two TH and KT mixed up. KT36, right? On the tower he just put up. He's got about a maximum gain of 16 dBi at about 14 degrees. His figure of merit is 12.7 at 20 meters, and it's about 17 dB better than me. Okay, so that's an awful lot of S
You might
units.
know
Yeah. So,
Well, this antenna says dipole, and what does Phil have
well,
on
mine's a
the tower?
dipole. He's got he's got a 5 element,
Okay.
and I just compared it to a 3 element. I probably should have made that a 5 element, but it was an intermediate kind of thing.
And fewer mountains.
So yeah, basically, Phil's got a much better pattern. He's got much more gain. So if you compare, let's just say comparison like at 16 degrees, I've got 4.5 dBi, and he's got about 15 dBi. So there's a almost 10 dB greater.
So you're
signal.
working out of the noise, and he's got a clear signal.
Yeah.
So to confirm that, I have a hex beam in Carbondale. I have a hex beam at the cabin. And I've got the remote set. And I get 4 to 5 S units difference on the same signals.
Yeah. Is that hex beam act sort of like a tri-bander in general?
Well, yeah, it's a
3 element, I mean?
though.
Yeah. I
Yeah.
meant to say 3 element.
It's like a 2-element game.
Oh yeah. Okay. So and here's the terrain that shows you the difference between mine and Phil's terrain. And no wonder he has much better coverage of the low angles. Okay. So this is a nice comparison, and here's an example where I took away the statistics because it didn't make any sense, because you could only have one statistics file and you're looking at 4 different azimuths, so that doesn't make any sense. But this is nice because it shows you the change as Phil's antenna goes around, the 4 points of the compass. What does it look like? And the terrain profile is over here on the right. I'm going to not spend a lot of time on here, but you can look at these when they get on the website and look at just compare the different terrains, and you'll kind of see that this rise here at 270 is what causes this low gain down in here. This fall off at 90 degrees is what gives him this big bump here at the low angles, because he's getting reflections off the front of that decline. And then this red one, which is his 45 to Europe, almost looks like a dipole, nice and symmetrical because it's almost flat. If you can see the red line in there, that's for the first initial distance, it's nice and reasonably flat. So he gets it basically as though we were in a dipole in flat territory. I mean, much better gain than a dipole, but basically that response. Okay, here's N0KE, KQ0C, and K0ALT to Europe. The big takeaway, I mean, the N0KE's figure of merit is about 4 dB better than a tri-bander over flat. Okay, these are sort of the takeaways from this. I tried to use the right antennas in terms of height and number of elements. I may have gotten one or more of these wrong, but the general idea is really just to compare the fact that there's different terrains here, and I'll show you those in a sec. KQ0C's cliff improves the response at low angles. It's about 2 dB better for a figure of merit. Now remember, the figure of merit is over all angles, so it doesn't get to just claim that, well, because I've got almost 10 dB better at 1 degree, that measures everything. That only works 6% of the time. That only works about 6% of the time. But so the overall figure of merit is better, and it's because of this predominant gain here. But the other thing to take away from this is the gain that he gets here. Oh, I should use a mouse. The gain that he gets down in this angle, these angles here, is really taken away from the gain here. And that, you can't do anything about that because there's only so much energy out there, and your antenna responds only to certain, I mean, it basically has the same amount of energy to respond to. If it's doing a better job at one angle, it's got to do a worse job at another angle. There just isn't any way to get around that. And K0ALT looks into the hogback, so you can see she's got a cutoff angle here about 7 degrees, which is very much similar to what I have, my problem, and she's got a similar kind of thing. Here's, it's not as bad as mine. Her line of sight is 7 degrees, so she gets a little bit. And the terrain, it gives you a real difference. Here, the blue is well, let's go with the notes here. These are very highly exaggerated, remember, because the scale on the left is only about 2,000 feet, and on the bottom is 15,000 feet. So you can make it so that these look similar, and you'll get a better idea of what the terrain really looks like. But from the perspective of understanding what's going on here, this graph gives you that information. The 20% slope at KQ0C dominates the terrain effects, and toward, this is again, this is toward Europe, 40 degrees. So you see that fall off really dominates his responses at low angles. And Christine has got the hogback sticking up here, and that really impacts her. Again, the distance that's shown here is the 4,400 meters that we set in the microdem program to generate the profiles. Okay, now just a quick look at stacking effects. And this is at Phil's house, trying to say, well, what would happen if we, now this is on not the tower that he has, but the tower that's up north, a little bit north of his other tower, and the blue is what his current 60-foot 5-element looks like. Okay, and again, this is toward Europe. Then what happens if we add another Yagi and we moved it, put one up, a new tower, of course, at 120 feet, and that gives you improves the low angle maximum gain a little bit. Where am I looking? I'm looking here. Yeah. But you get this big null at 22 degrees, and this is often a problem with raising an antenna too high. Is that the lobes get so compressed that the nulls start to creep into the pattern, and they can be very significant. I mean, if you were trying to talk to somebody in Massachusetts, the angle might be much more like 20 degrees. Okay, so and you'd be cutting out things. So you want to say, well, what can we do about that? Well, one thing you can do, and that's why stacks have become three antenna stacks have become useful, is that if you put another Yagi at a lower angle, I mean a lower height, you can actually pull that high end back up. Okay, so the green one shows you if I have all 3 antennas in place with a low 30, 60, and 120. Okay, and we could have done, the numbers were just pulled out of a hat, and you would want to play with those because they might have very different effects on the propagation. But a three stack really gives you great coverage, even out to about 25 degrees. And there aren't any signals out at 25 degrees, so it doesn't matter.
And it increases the overall gain.
Yeah, and the figure of merits, you can see, while the figure of merit for the single antenna is 12.5, the figure of merit for the second antenna gives you 15.2 because you still have good coverage of the large percentage. And again, if this had been an azimuth where this had been important, you would have seen a fall off in the figure of merit probably. But it doesn't matter. And then when you add the third, you don't get much better coverage because the gains over these most important angles are not that different. Okay? So you can get terrain data from the National Elevation Database, use microdem to process it and produce terrain profiles. The high-frequency terrain analysis program consumes those profiles and also takes elevation statistics that have been generated by VOACAP to calculate the resulting antenna response, gives you a figure of merit. The terrain assessment can be a really important tool when you're picking a QTH or when you're designing an antenna installation, and I'll be happy to take any questions that you might have. It's 12:09, so thanks for bearing with me.
How do you know what would be the optimized height to put your antenna at? How would you determine that?
Well, generally, one wavelength is a good place to start.
Right.
See what kind of-
And then you just use a program like HFTA, just move it up and down and see, But again, you want to do that for multiple
So what's the
azimuths to
going-
make sure you don't do something that really screws up. But I think it's easiest to put up antennas in Kansas. Okay. Dean Straw would say the easiest place to do terrain analysis is in the flat. Because
It's
you
an idea,
get rid of all
basically it
that
helps you.
terrain effects. You just say, how high, yeah, then you can go just do the height. Do it over flat, put it the height and see what it looks like. The terrain is gonna kind of color things out.
I'm not sure I can understand the
That's
results.
how I go.
But just like Ash can't really modify it to make it better for higher angles. He's stuck with that value. So it's predetermined.
Unless the